So what all do you guys remember from last class about molecular orbital theory? Yeah. Yeah, go ahead, Ritu.
So when like the molecular orbitals, they fit, like they also go by like of molecules of comparable energy.
Yes.
Where the lower ones fill first and then the upper ones.
Absolutely. We'll start from the beginning.
And like
how are molecular orbitals formed? Like how do you get molecular orbitals?
when atomic orbitals of the same energies combine, like
Yes.
of the same energy level.
Yeah, you can
Like
say
only S with S and not like S with P or S with D.
absolutely. So atomic orbitals of comparable energies combine to give molecular orbitals. All right. How many types of molecular orbitals are formed? Like if you have two atomic orbitals, which are like two electron wavelengths combining with each other, so they can combine in two ways. So constructive way and destructive way. When they combine constructively, what do you get? When they combine destructively, what do you get?
So you get a bond, you get like a bonding orbital.
Yes.
Because like their waves are in phase, and when they're destructive, you get an anti-bonding orbital.
Correct. So when they're in phase, constructive combination will give you bonding, destructive will give you anti-bonding. And between both of these, like what's the difference between a bonding orbital and an anti-bonding orbital? Kaveri?
Bonding is more stable.
This is more
That's
stable.
lower energy,
And
lower.
anti-bonding has a higher energy compared to.
but more unstable.
Correct. So anti-bonding is unstable. This does not favor bonding. So this does not favor bonding. So this is unstable. And this has a higher energy. This is a higher energy level. Okay. Awesome. And do you guys remember the order of bonding and like the order of different molecular orbitals, energy level, the energy order?
Yes, ma'am.
Yes.
So there was like 1s sigma and then 1s like anti-bonding sigma bond. Then 2s also has like a sigma bond.
Yes. So
then there was
first we start off with sigma 1s and followed by anti-bonding sigma star 1s. Then yes, sigma 2s. Then
sigma star 2s.
sigma star 2s. Okay. उसके बाद
sigma 2p.
sigma
there was pi 2px.
sigma 2px उसके बाद pi 2p हाँ
pi 2px and pi 2py.
Pi 2p.
So you have pi 2px equal to pi 2py. Both are at the same level. Followed
and
by
then they're anti-bonding.
Sigma 2pz. So this is for everything. The anti-bonding one, Ritu, you were saying. So these two get interchanged. You get sigma 2pz for oxygen and fluorine alone. And it's like once all the 2p orbitals are done, then you go to the anti-bonding part of it. So iske baad the same thing. So you have pi star 2px equal to the pi star 2py followed by sigma star 2pz. Okay, this is what's happening with this. This is the order of molecular orbitals. So this is the order in which the electrons are filled up. So very, very similar to atomic orbitals where the 1s is filled, उसके बाद 2s आएगा, उसके बाद the 2p orbitals आएगा. The only difference between the atomic orbitals and molecular orbitals is that you again, because these are related to chemical bonding and all that, you have the pi, like this particular part you need to take care of. Usually the pi orbitals are filled first, but specifically for oxygen and fluorine, in the case of oxygen and fluorine, these two are exchanged. So this is for oxygen and fluorine. The sigma is filled, uske baad pi is filled. The anti-bonding, the order will remain the same. Okay. So we'll practice electronic configuration of the first few elements, and uske baad we'll talk about how is molecular orbital theory helping us in figuring out the stability and magnetic properties and all of those other things. Okay. In case you guys have this noted in your book, let me know either from today or from last class. Then we'll get on to the electronic configuration part.
We haven't noticed this down.
Okay. Okay. Awesome. So first element, you have hydrogen. So if you were to figure out the molecular orbital theory configuration for H2 molecule, so the first one, atomic number 1, we're going to look for H2. Hydrogen ka, like each hydrogen atom, what is the electronic configuration?
1s1.
Yeah.
1s1.
You just have 1s1. So एक ही electron है, एक ही orbital में. So that single electron is going to, so you have one H atom ka 1s at this level, दूसरा H atom ka 1s at the same energy, because hydrogen, same atom. So this single electron, initially they were like this. Based on molecular orbital theory, if this is the energy level, on combination, you get two molecular orbitals, one bonding orbital at a lower energy and anti-bonding at a higher energy. And we have two electrons. So this is the bonding, so sigma 1s. This is anti-bonding, sigma star 1s. Two electrons hai. As Ritu said, it follows the same rules and principles of Bohr rule. Lower energy gets filled first. Hund's rule, pairing, and Pauli's exclusion principle. Following all of that, both the electrons will occupy the same orbital with opposite spins. So this is the electronic configuration. So just like with atoms, if you had to write the molecular orbital electronic configuration, then for H2 molecule, this is how you'll write it. For H2 molecule, the two electrons, there are two electrons occupying the sigma 1s orbital. So you'll write it as sigma 1s2. So atomic इसमें 1s orbital में एक electron है, so you've written it as 1s1. अभी sigma 1s orbital में दो electrons है, so you'll write it as sigma 1s2. Okay. Similarly, can you guys work it out for He, helium के लिए? If we were to look at a molecule of the form He2, helium having electronic configuration of 1s2, can you figure out the molecular orbital configuration for helium? The diagram will be the exact same. So instead of hydrogen, you'll have the details filled up for helium. once you figure this out, you can send the electronic configuration on chat if you want, or you can like say it out. We can discuss this. We're considering He2, so that's 2 atoms of helium. So the energy level diagram will be very similar to what you have for hydrogen. So you have 2 helium atoms. So this represents the 1s orbital. Now He2 molecule ke liye, again the same thing. If 1s combines, you get 2 of these, the anti-bonding at a higher level and bonding at a lower level. And it's the exact same thing. So this is again sigma star 1s, so sigma 1s. Oh, Ritu has already got it, yes. So total, abhi, each helium has 1 electron originally, 2 electrons originally, right? So this is paired up over here, this is paired up over here. So when the 2 helium atoms combine, you have a total of 4 electrons. So 4 electrons combine, like when, yeah, you need to distribute 4 electrons in these energy levels. Okay, Ritu got it. Others, Arnav, Adat, Kaveri, Smera, any of you got it? Rishit, Sanat. Kya ho raha hai? Like, did you get it? Like working it out? Oh, Smera has also got it. Yes, configuration is absolutely right. Aa gaya. So far Ritu and Smera have solved it. Arnav, Adat, Rishit, Sanat, Kaveri, what about you guys? Adat, total 4 electrons hai na? And when we're talking about molecular orbitals, after combination, you get sigma 1s, sigma star 1s, right? So your configuration also should mention if it's sigma or pi or what is the thing. 1s2 is helium atom ka configuration. Abhi agar do helium combine हुए, तो फिर क्या होगा? So you have sigma 1s and sigma star 1s. I have a total of 4 electrons. तो पहला electron कहाँ पे जाएगा? Kaveri, sigma 1 is again, the rules followed are the same as your atomic orbitals, because each box can hold only 2 electrons and both the electrons will have opposite spins. So sigma 1 is 4 is completely impossible. See, everything is same as what you had learned for atoms, atomic electronic configuration. The only difference is that yahan pe the names have changed. So instead of 1s, 2s, 2p, you will have sigma 1s and sigma star 1s. Your bonding and anti-bonding orbitals are formed. Kaveri, now the second answer that you sent, that is absolutely right. You got it. All right, Arnav, Sanat and Rishit, where are you guys at?
I'm not sure if mine is correct.
Send it, no? Then I can check. यहाँ तक did you guys understand क्या करना है? Like you have two individual atoms and each orbital, like 1 plus 1, you need to get a total of 2 molecular orbitals, and both of them, one is bonding and one is anti-bonding. Rishad, that is absolutely right, whatever you said. Iske baad, filling up the orbitals with electrons is same as whatever you did in your atomic structure ka configuration. Sanat, you sent half of the answer. So if I have two helium atoms, each has 4 electrons, each has 2 electrons, which means I have a total of 4 electrons. So you have filled in 2 of those electrons. So remaining 2, where are you going to fill? Arnav, you made the same mistake as Kaveri. I was just telling her earlier. Each box, like this is something you learned in atomic structure. Whenever you have an orbital represented by a box, each of these boxes, how many electrons will it take maximum, Arnav? 2, right? So idhar bhi, I have sigma 1s and sigma star 1s. Each of those is a molecular orbital represented by a box. So even these boxes can take a maximum of 2 electrons with opposite spins. So 1s4 is something that is impossible. You will never, like, don't even think about it. Whenever you write electronic configurations, S4 kabhi nahi hoga. Okay. All right. So you have 4 electrons. Lower energy level pehle fill karna padega. So 2 electrons go here with opposite spins. And so that's like 1, 2 are done. Remaining 3 and 4, electron 3, electron 4 hai na. Remaining 2 will go into the next available orbital, which is sigma star 1s. So again, the same thing, opposite spins ke saath, 2 electrons here. So if I write the electronic configuration, so start from the lowest energy. So lowest energy hai mere paas sigma 1s. Usme I've got 2 electrons, so sigma 1 is 2. Uske baad fill hua sigma star 1 is 2. So this would be the electronic configuration. Sigma 1 is 2 and sigma star 1 is 2. Got it?
Yes, ma'am.
All right. Arnav, clarified?
Yes.
Okay. The next one, for lithium, you guys only do it. So if I consider Li2, iska electronic configuration kaise hoga? So lithium originally atomic configuration is 1s2 and 2s1. So atomic number is 2. So it has 3 electrons. So this is how it's distributed. Usme ek 1s orbital hai aur ek 2s orbital hai. So no hints, you guys try and work it out. If you're stuck somewhere, if you don't know how to approach it, let me know and I'll do it over here. So the energy diagram also will be the exact same. Because we dealt with 1s, there's only like one box here. This represents 1s. Now, since we have 1s and 2s, you will have both the boxes. So higher energy may you have lithium ka 2s. Uske niche, lower energy, you have the 1s orbital. The rest of the details remains the same. When 2 1s orbitals combine, you get 2 of the one bonding, one anti-bonding. Again, same when 2 of the 2s orbitals combines, you'll still get a bonding and an anti-bonding. So total, you'll have 4 molecular orbitals, and you need to fill 6 electrons in them. Very nice. Kaveri's already figured it out. Smera also got it. Nice. Now you guys got into the zone. Arnav also got it. Correct. Sanat also sent. So 4 people done. So Rishit, Ritu and Adit. Rishit also got it. Absolutely right. Ritu also sent it. Correct. So Adit, what is happening? What's 1s2 sigma start and then sigma 2s2. Nice. All of you got it. Very good. Actually, you guys are drawing these energy diagrams, right? So make a note of it, because in case you presented a question from this format, you guys need to have that understanding. You need to be able to understand and interpret this. Okay. So lithium, 1s2, 2s1 है. So 1s2 may you have 2 electrons, and 2s1 may there's only 1 electron each. So these two together, first fill up these, next fill up this one, and then the remaining gets paid up here. So electronic configuration, you have sigma 1s2, then sigma star 1s2, and then sigma 2s2. So this is the electronic configuration for lithium, which all of you have got it. Okay. So have you guys drawn the energy diagram?
Yes, ma'am.
Yes,
That is
ma'am.
Yes, ma'am.
Okay. In that case, we'll
Yes,
go to
ma'am.
the next part. So this is how in your syllabus you're given, like from hydrogen all the way to neon, first 10 elements ka. This is the exact same pattern that you'll follow. 1s, 2s. Uske baad 2p ke liye you'll have separate levels for 2px, 2py and 2pz. Okay. So for every orbital of a different energy, you're going to draw these diagrams as it. So before we start with the p orbital, like I'll pick oxygen as a special case to discuss. But before that, there are a few characteristics that we can figure out from
ma'am.
molecular orbital.
Ma'am, can you hear me?
What's up?
So another one.
So like I had a doubt ki when concerning atoms, and like if we have to write the electronic configuration of like extremely big elements, like we use like short methods, right? Like we use the first, like the noble gas before that element, and then we write
Yeah.
just the minimum part of it.
Yeah, absolutely correct.
So is there something similar in this also?
Not right now. Like again, we are working only with the simple elements right now, only till neon, and till neon, other than helium, there's no noble gas as such. So you'll have to list it out like pura 2p tak.
Okay.
Ma'am,
Yeah.
ma'am,
Yeah, Ritu.
like when we were like doing this at school, they also taught us like to write that KK dash thing. Could you like clarify that a little bit also?
Which one?
They told us to like write like KK dash and then just like write the end of it, like the configuration.
Oh, okay. So the first orbital is K, and then the anti-bonding one represented as K dash, that way.
Yeah, I just wanted to clarify, is it just like the first one also like the 2s orbital?
This K dash, LL dash, I'm not 100% sure of. I'm not confident. Just give me some time. I'll just recheck some things and I'll let you know about this notation.
Okay, ma'am.
Ma'am,
Yeah.
in the previous class, after we did like intermolecular hydrogen bond and intramolecular hydrogen bond. After that, we did molecular orbital theory, right?
Yes.
I think because there was something in my okay. So right after we didn't do anything in the middle, right?
No. Hydrogen bonding, like the consequences of it, and then we started with molecular orbital theory.
And did that come under Fahan's rule, or is that a separate thing? Hydrogen bonding ka?
That's a separate thing. Like Hund's rule and all are relevant only for electronic configuration, either for atoms or for molecules. Right?
No, I'm talking about Fahan's rules.
Fahan's rules. Fahan's rules is relevant or it's applicable for ionic compounds.
Oh, okay. Yeah.
All right. So molecular orbital theory, based on the electronic configuration, you can figure out some characteristic properties of the molecules. So the first property we have is stability. Like if a molecule is formed, is it going to be stable or not? So stability this is the criteria. So if the number of electrons that you find in bonding orbitals is greater than the number of electrons that are contained in anti-bonding orbitals, then the molecule is stable. It will be formed and no issues. You know that, okay, that molecule exists in reality, it is capable of being formed. And similarly, iska converse, if anti-bonding there are more electrons and in bonding there are less electrons, then the molecule is unstable. Okay. So for example, hydrogen the total number of electrons in bonding orbitals is, we have 2 electrons over here. So bonding we have 2 electrons, and anti-bonding we have 0 electrons. So because there's more electrons in bonding than in anti-bonding, then H2 molecule will be formed and it is a stable molecule. In this case, the number of electrons in bonding is equal to the number of electrons in anti-bonding. So let me just modify this. If it is greater or equal, then that molecule will not be formed. It's going to be unstable. That is why in reality we can say that He2 does not exist and He will not form a bond with another He molecule. Sorry, another He atom. Similar. Simple. So if you have more electrons in bonding than anti-bonding, then the molecule that is formed is stable. Like that molecule will be formed and it is going to be stable. But if you have more number of electrons in anti-bonding orbitals, then that molecule will not be formed and it's going to be unstable.
But wouldn't that be like impossible to happen, because always the electrons will first go to the bonding one?
Not necessarily. Yeah, like that is true. That is the reason I'm showing it. Like that's why we are looking at cases over here, right? So hydrogen ke case you have more number of electrons in the bonding orbitals, 2 electrons in bonding, 0 in anti-bonding. So H2 molecule will be more stable than individual hydrogen atoms. In the case of helium, that is not the case. You have equal number of electrons in bonding and anti-bonding. So you can say that, helium ke case the He2 will not be formed, and even if it does, that is a more unstable state. That's why each of these He atoms will not prefer forming a bond with each other. And that's why helium is inert.
In this case, they are equal, but how is it possible that the bonding is less than anti-bonding? Because it has to be filled before a mean.
Equal, because of the number of electrons. Like it, depending on the number of electrons and number of orbitals that are formed, you'll have different cases.
Yeah, but like in what case will the anti-bonding electrons be more than the bonding electrons?
Maybe in some of the higher elements, we'll have to see. If you look at two px orbitals, like the p orbit, two p orbitals, the bonding and anti-bonding orbitals being formed, again, it's going to get filled up in the bonding first, and then it's going to get filled up in the anti-bonding. I'll have to look at it, like we'll have to take a case by case basis, but this is a general rule. Like if at all you come across a case where there's the number of electrons in anti-bonding is greater than or equal to the number of electrons in bonding, then that molecule will not be formed.
So is it like in the D or the F orbital that maybe it changes a little bit?
Possible, yes. Yeah. But this is the general rule, like based on molecular orbital theory, if you have to assess the stability of any molecule, this is like the first check you're going to do. How many electrons do we have in bonding and how many electrons do we have in anti-bonding? So agar bonding mein zyada hai, then it's going to be stable. Otherwise, it's going to be unstable. Okay. Next, based on the number of electrons, you can also check the bond order. Okay, so the bond order, BO, you can calculate it as half into the number of bonding orbitals minus the, not number of bonding orbitals, this is the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals. So bond order is equal to half of the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So if you relate this formula with the stability wala thing, you can see that if the number of bonding orbital electrons is greater than number of anti-bonding electrons, then you'll get a proper bond order. You'll get the bond order to be 1 or 2 or 3 or whatever. But if the number of anti-bonding electrons is equal, then the bond order becomes 0. So bond order 0 matlab single bhi nahi, double bhi nahi, triple bhi nahi. So there are no electrons shared between them. Matlab molecule form nahi hua. And if it is greater, then this whole value becomes negative, and it's like the way you interpret is those two atoms are like actively repelling each other. Yeah, so this is another thing you can figure out. And the third characteristic you can figure out is the, based on the bond order only, like it's an extension of this. So if bond order equal to 1, then it's a single bond. If bond order equal to 2, then it's a double bond. And if bond order equals 3, then it's a triple bond. Same thing. Yeah.
Sorry, I lost connection when you were talking about bond order.
Like at what point?
You were explaining the formula half of something and then I got disconnected.
It's whatever is noted here. So half of the number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals. So you can, logically look at it. If you have greater number of bonding electrons, then this is going to be a positive value. You're going to get like 1 or 2 or 3 or 1.5 or like whatever it may be. But if they're equal, bond order becomes 0. Matlab, 0 matlab there are no electrons shared between them. Matlab koi molecule form nahi hua. And if number of anti-bonding electrons is greater, then this is going into negative, which also does not make sense. So that also tells us that, yeah, there is no molecule formed between these atoms. And extension of this, based on the bond order, you can figure out what type of bond. If it is 1, it's a single bond. If bond order equals 2, it's a double bond. If bond order equals 3, it's a triple bond. And in molecular orbital theory also, the same rules apply. For bond length, single bond is greater than double bond, greater than triple bond. So अगर single bond है दो atoms के बीच में, they will have the maximum bond length compared to double bond, compared to triple bond. Next, this is the most important property. Based on this, you'll be asked a lot of questions. So this is the magnetic nature. Again, just like how we figured for elements, even for molecules, based on the electronic configuration that you get from molecular orbital theory, if there are unpaired electrons, then that particular molecule or that particular substance is going to show paramagnetism. And if all the electrons are paired, if there's like 0 unpaired electrons, then that's going to be diamagnetic. Do you guys remember what do you mean by paramagnetism and diamagnetism?
I forgot.
I found it very confusing.
Oh,
Paramag-
like if you just had to remember it, you can think of it this way. Paramagnetism is the substances are attracted to magnetic fields or magnetic forces. And diamagnetism means they are repelled. Okay. So what happens is, like, there's a good meme also that explains paramagnetism, diamagnetism. So when you take that element or a compound or whatever, when you take that substance and put it in a magnetic field, do you guys remember what is a magnetic field?
It's formed due to like flow of electrons, like where you can feel the effect of the magnet.
Correct. Flow of electrons, yes, electricity and magnetism are kind of related. So magnetic field affects electrons, which is why electricity and magnetism are basically related. Magnetic field is formed because of flow of electrons, but that's not the primary cause of it. Like, sure, electricity does produce magnetic field, but magnetism is its own thing. Like, you have magnets. The cause of magnetism is not known as such. Electricity is one of the causes, yes, but magnetic, like, you do have magnets without any involvement of electricity. Also, you have natural magnets. So magnetic field is basically the field, or it's basically like a force field that occurs because of a magnet. Like if you have a magnet present here, like bar magnet has like a field that has like this kind of a shape. So these are called magnetic field lines, and they give you an idea of, you know, like what is the direction of the force and what is the magnitude of the force and all of those things. So it's basically like a force field that occurs because of the presence of a magnet. Now, when you take a random substance and place it in a magnetic field, then it may or may not get affected. So that depends on the substance. So if it is attracted to the magnetic field, at the atomic level, what happens is you have the electrons that are spinning in their own orbitals. They're undergoing their same, whatever, their own motion, right? Like their rotation, they're moving, all of that stuff. When you place them in the magnetic field, the electrons all, it's like when you have an assembly of people, when there is nothing, like people are just milling around. But if somebody calls for an attention, like school assembly jaise, then everybody, you know, just stands in one straight line, right? So that's what happens to the electrons also. If they are paramagnetic, if they are affected by magnetic field, if they're attracted to the magnetic field, all the electrons get aligned along in a single direction, depending on, however the magnetic field lines are. So they are affected or they're attracted to the magnetic field. So if they show that kind of behavior, then you call that substance to be paramagnetic. If the amount that they're affected is so much, like what happens to iron in the presence of a magnetic field, like you can literally feel the force, like iron nails, if you have a magnet close by, it literally attracts the iron, right? So forces at that level is called ferromagnetism. But if it is not that much, like it shows, you can't visibly see it, but it is definitely affected by magnetic field. It is, the electrical properties of that substance is changed because of the magnetic field, then that is called paramagnetic. But if it does not show any such effect, if it is not attracted to the magnetic field, or maybe if it is like repelled, then that particular substance is called diamagnetic. And diamagnetism happens when all the electrons are paired up with each other. Paramagnetism happens when there are unpaired electrons in that particular substance, be it the element or the compound. Yeah. Like
So
even
the electrons get like attracted.
the electrons are affected and they all align themselves in a single direction within the atom. The substance is attracted to the magnetic field. See, even if you don't understand like what happens behind it, you just need to know this much minimum, that if there are unpaired electrons, then that makes the substance paramagnetic, and paramagnetism means they are affected by a magnetic field. If all the electrons are paired up, then that means the substance is diamagnetic, and diamagnetism means they are not affected by the magnetic field. They are not affected, or they are like basically repelled by the magnetic field. Okay. That's basically the gist of what you need to know. Paramagnetism means they are affected by a magnetic field, and that happens when there are unpaired electrons present. Diamagnetism means they're not affected by magnetic field. In fact, they're repelled by the magnetic field, and that happens when all the electrons are paired up. So if you're looking at it for specific elements like metals, like iron or whatever, then you should look at the atomic configuration, like the electronic configuration of the atom. And if you're looking at molecules, like for example, whether nitrogen is paramagnetic or diamagnetic, or whether oxygen is paramagnetic or diamagnetic, in these cases, then you'll need to look at the molecular orbital electronic configuration. Okay. Yes, hello.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
All right. As an example, let's look at the electronic configuration of oxygen only. Energy diagram of oxygen. Okay, so this is the molecular orbital diagram for oxygen. So here you can see that only the 2s and 2p are shown. 1s is the same as 2s, like it has a lower energy. You can see it like niche और भी होगा. You have sigma 1s and sigma star 1s. उसके ऊपर then you have 2s के लिए sigma 2s, sigma star 2s, and these are the 2p orbitals. So oxygen, wait, is this oxygen? I'm sorry, this is for O minus. This is for O2 2 minus. This is the peroxide ion ka this thing. I'm sorry, wait, let me look for oxygen specifically. Yeah, this is oxygen. Yeah, so 2s ke baad you have 2p orbitals, and according to oxygen's order, you have sigma 2pz first, followed by pi 2px and pi 2py. They have equal energy, so that's why it's represented like this. And then you have the anti-bonding orbitals. Now 2p may you have 4 electrons each, so 4 plus 4, total of 8 electrons, which are distributed in these orbitals. Again, as per the rules, so first the sigma 2pz, both are paired up. Then when you're filling up the pi orbitals, equal energy hai, so first these two get filled up, and then these two get paired up. So that's 6 electrons total. And then pi star, because they're equal in energy, each remaining electrons are distributed over here. Okay. First thing, 1 second. So you also have 1s, and like iske niche you have the 1s also present, just like with hydrogen, helium, lithium, all of that. So 1s also gets filled up. So sigma 1s may you have 2 electrons, and sigma star 1s may you have 2 electrons. Okay. So based on this diagram, yeah, Kaveri, what's up?
We don't make a different one for Z.
We made it, no? Like यहाँ पे sigma 2pz है, उसके ऊपर you have 2px and 2py.
No, like we don't make a different diagram for it.
No, because when you're looking at the atom, if you consider a single atom, 2p may all three have equal energies. So px, py, pz have equal energies. That's why they need to be at the same level. Only
so whatever has the equal energy has to be put into the same diagram.
Correct. Because y-axis represents energy, right? So if you put it anywhere upwards or downwards, that would mean that, oh, that particular orbital has a higher or lower energy, which is not the case. When it's as an individual atom, px, py, pz all have the same energy, so they have to be at the same level over here. Or like,
also, do we make this diagram? Do you draw this?
You can make this, yes. So this is for oxygen molecule. For O2, this is the representation. Like just like how you guys made for helium, lithium, and hydrogen. As you keep going, nitrogen, fluorine, whatever, this is the specific one is for oxygen. So you can see here, left side represents one oxygen molecule, right side represents the other oxygen molecule. Beech mein the molecular orbitals belong to oxygen molecule O2 over here. So the 1s will have to come below 2s because that would be lower in energy. So let me know once you guys are done drawing the diagram, then I'll ask some questions based on this and you guys will need to answer. Okay.
Isoelectronic molecules and ions will have identical bond orders. I didn't understand that.
I'll come to that in a bit. Okay, let me complete molecular orbital theory here. Another extension of this is, are you guys clear with figuring out the electronic configuration and the energy level diagram for molecules? Like if I were to give, like this is the structure for oxygen. If I ask you to do the same thing for N2 or F2, will you guys be able to do it? Like, do you know how to approach it, how to start it?
Yes, ma'am.
I guess.
I think so.
Yes, ma'am.
Okay, good. Because this is, so far we've been dealing with neutral molecules. What if I ask you about the molecular, this molecular orbital diagram for O2 2 minus. So this particular ion is called the peroxide ion. You guys are familiar with hydrogen peroxide, right? H2O2. So
Yes, ma'am.
yeah, H2O2 contains the peroxide structure. Its structure is, you have two oxygen molecules and each of these has a negative charge. So in peroxide, each of these is bonded to hydrogen. That's why you get H2O2. But otherwise, this also forms ionic compounds. Like you have sodium peroxide, you have potassium peroxide. Peroxide is a ion that you find in compounds. Okay. So now if I ask you, peroxide ion is it paramagnetic or diamagnetic? How will you answer this? Like, how would you approach this question?
Diamagnetic, because since there are two electrons that are unpaired, and then it's 2 minus charge, so then 2 get added, so they'll be all paired.
Absolutely, Kaveri, you got it. That's exactly how you'd approach it. So peroxide is made up of O2 and then this 2 minus, right? So this 2 minus represents that there are 2 extra electrons. So you have the regular normal energy diagram for oxygen, and the extra 2 electrons will be accommodated in, again, just continue filling it up with the other 2 electrons. So these two will be paired up. Let me use a darker pen. Yeah, so these two will be paired up here. And yeah, that's why you get this thing. That's where you can figure out the electronic structure from. Okay. Let's practice one more question, one last one. Okay. Let's say you have this particular, so I'm giving you C2 minus. So Iska, let me know what is the bond order. And based on this, if you can figure out, if it happens to be that, this is a stable structure, iska proper positive bond order aa raha hai, then let me know what is the magnetic nature of this.
Do we draw the diagram for this too?
Yeah. You can draw the diagram, but if you think you can directly write down the electronic configuration because you remember the order, you can approach it directly also. But I just need the final answer. What is the bond order and what is the magnetic nature? You just need to tell me these two quantities. Whether you apply it directly to the configuration or whether you draw the energy diagram is up to you.
Ma'am, do we put it in the chat?
Yeah. So you can directly send me bond order equal to and magnetic nature is. Agar bond order so if
without drawing the diagram, how do we know the bond order and all that?
Bond order formula diya na? So total number of minus total number of anti-bonding.
Okay.
See, even when you're writing the configuration, bonding is just represented by sigma pi. Anti-bonding is represented by sigma star and pi star. So that way also you can figure out the stuff. I was saying, send me the answer as bond order equal to this much, and then just send me paramagnetic or diamagnetic. If at all you're not getting a proper bond order, अगर negative आ रहा है या फिर zero आ रहा है, in that case just say the species is unstable or does not exist. Ritu, bond order cannot, I can't imagine bond order can be 5. Maximum you have single bond, double bond, triple bond, right? In the case of resonance, thoda idhar udhar ho sakta hai. Check your calculation, Ritu.
I forgot to half it.
Okay. Arnav has sent bond order. To send the nature also, Arnav, para or dia. Sanat, I mentioned C2 minus here. I don't know if you took this into consideration.
Oh, I forgot the minus.
Hmm.
Ma'am, I have a doubt.
Yeah.
Do you use the minus like once you've got the final bond order, or do you like add it while you're finding the thing? Because I'm getting like a fractional answer.
Chalega. And that means that, you know, it's like a resonance structure or something and stands for something else. Cool. Arnav and Adit and San. Oh yeah, Sanat I already mentioned.
Oh
Guys,
wait,
remember-
one sec.
Yeah. अगर unpaired electrons है तो para होगा, अगर सारे electrons pair up हो गए तो dia होगा. C2 I can like, because of that extra minus, I can literally see that there's odd number of electrons. Odd number मतलब कहाँ से pair हो सकता है? Like there's always going to be one left.
How do we figure out the magnetic nature? I didn't understand.
Simple, if there's all the electrons are paired. So suppose you didn't draw the electron energy diagram. Suppose
Yeah,
you're
yeah.
just doing this sigma 1s2, sigma star 1s2, then sigma 2s2, sigma star 2s2. यहाँ तक 2 plus 2, 4 plus 2, 6 plus 2, 8 electrons हुए ना. C2 मतलब total of 6 plus 6 plus 1. So that's 13 electrons. Hai na? So this way, when you're writing the electronic configuration, suppose you come to a point where beach mein you have pi px, pi 2px equal to pi 2py. Hai na? So when they're equal in energy, they get filled up simultaneously. So hamesha you have pi 2px1, then pi 2py1, and then agar or electrons hai, so then one by one this gets paired up. So in the process of writing the configuration, if you come across any orbital where 2 electrons are not there, you see that there's only 1 electron in that particular orbital. That means that that electron is unpaired. Agar 2
Got it.
electrons hai, to maximum fill up ho gaya, so that's paired up.
Ma'am, could you check my bond order answer?
Rishit and Kaveri have to check their bond order. Baki sabko, like you guys got the same thing. Adat, yes. Abhi jo bheja hai, 4 o'clock that I'm seeing, that is correct. Arnav, yeah, you corrected magnetic nature. Smera, yes. Rishit, your magnetic nature is correct. Bond order, check the calculation. Ritu, yes. And Kaveri, हाँ, I think like math में ही कुछ तो गड़बड़ हुआ है, plus minus 1. Just check that. Okay, rest of you all, like Sanat, हाँ, now whatever you calculated, you got it right.
Ma'am, I sent the text like 2-3 minutes ago.
401 अभी आया. Rishit, अभी जो भेजा है, yeah, that is correct. I think you corrected it. So bond order आना चाहिए 5/2. Like that's what I've been seeing from everybody.
Even if the orbitals are half, like each orbital has one electron, even that is considered as para.
Yeah, if there's one electron, it means that there are unpaired electrons. So that's why it's para. If there are 2 electrons, it means that they're paired up. So that's why that's dia. Just to check, like verify your answers. Rishit, now you got it. 5/2 aaya. So this should be your configuration. Sigma 1 is 2, sigma star 1 is 2, and sigma 2s, sigma star 2s. Now, because this is not oxygen or fluorine, the pi orbitals get filled up first. 2p में there's 2 electrons each, total 4 electrons है. So 2px, 2py. And then C2 minus bola hai na, so that extra electron will go in the sigma 2pz orbital. So that's like a single unpaired electron. Okay, so bonding mein,
Ma'am,
yeah.
so like since our bond order was in fraction, does that mean the molecule is like unstable or something?
It's not unstable. There's some sort of resonance structure going on there. So that's how you can interpret it. Because only when there's like resonance structure, when the bond is between a single and double or between a double and triple, that's where you get like average, like all the parameters between the two bonds. Like that's what we saw in resonance, right? So when ozone existed in this way, it was neither a single nor a double. It was kind of like 1.5, and that's what your bond length, bond strength, all of that reflected. So that's kind
Okay.
of,
Ma'am,
yeah.
without drawing the diagram, how would you figure out the total number of electrons?
You will need to write the electronic configuration. If not the diagram, minimum configuration to pata hona chahiye.
But then if we take C2 minus, and so it'll be 1s2, 2s2, 2p3, right?
Sigma 1s2.
Like in the normal configuration.
So uske liye, so what you have to do is C2 minus hai na. So ignore the minus first. You have carbon. So again the same thing. So carbon made the 6 electrons. Because there are 2 carbon atoms, 6 plus 6, and then add the minus later on. So plus 1.
So I did like for one and then for the other and then I added.
Wait. So एक carbon में there's 6, दूसरा carbon में there's 6.
No, I took it like 7 and then 7. So I got 14 like that.
That's why you were off by 1.
Yeah.
But एक ही minus है ना. अगर C2 2 minus है, then you have 2 extra electrons and it's like 7 plus 7.
I thought it was like minus for each, so I did. Okay, I got it.
So yeah, so that's basically it for molecular orbital theory. So these are the kind of questions you guys are going to get, and a little bit of practice, and you guys are already able to answer questions. Thoda practice karne pe, even the silly mistakes and the doubts that you have, that's going to go away. Okay. So we'll take a little break. Abhi 4-6 ho raha hai na. So this year, organic chemistry is going to step up a lot compared to what you had in your 10th. In fact, This year, you're going to have volume wise relatively less than what you'll have in 12th. So only 2 chapters are dedicated for organic. You'll just have hydrocarbons part of it. And the first chapter, what we'll be starting off with is the basics of organic that you're going to apply in every single chapter later on. So this is the most important chapter that you will be doing this year. So we'll be coming back to the concepts that you learn this chapter, be it nomenclature. You'll be learning general overall properties like organic compounds may, what type of reactions they're going to undergo, and when a reaction takes place, what decides the direction that it needs to go in. You know, if you take an organic compound, put it in acidic medium versus basic medium, or alkaline KOH versus aqueous, like alcoholic KOH versus aqueous KOH, what decides, you know, or what decides whether a particular compound is stable, that is unreactive, or whether it's going to be highly reactive. So the basics behind all of this, you'll be learning in this particular chapter, some basic concepts and techniques of organic chemistry. So if you're good with this chapter, rest of your organic is going to be really, really easy. But if you don't pay attention to this particular chapter, then rest of your organic is going to be really, really difficult. Okay, so this is one of the most important chapters that you will ever study. The basic structure of overall organic chemistry, how you're going to study, is you have the basics right now, and then you'll be learning all about hydrocarbons right now. So you have details about alkanes, alkenes, alkynes, and benzene, aromatic compounds. Remaining, so in 12th standard, you will study about each and every functional group. So one chapter may you'll study about haloalkanes and haloarenes, that is organic compounds with a halogen in them, with a chlorine or a fluorine or a bromine in them. Another chapter will be all about alcohol, phenol, ether. Another chapter all about aldehydes, ketones, and carboxylic acids. And one more chapter all about amines. So that is nitrogen-based functional group. Okay. Any of these words ringing a bell for you guys? Alcohol, ketone, aldehyde, carboxylic acid, yes, sir?
Yeah, we had a
No,
list in
no.
10th grade.
Okay,
Yes,
you've heard of it.
The-
Cool.
Yeah.
Right? Okay. So that's how it's structured. You have basic hydrocarbons this year and each of the functional groups next year. All of the chapters, the pattern is exact same. You'll start off with basic nomenclature, like how do you identify and how do you name the compounds? And if there's any isomer, like isomerization, then what type of isomers and all of that. Do you guys remember isomers? Familiar with that word?
No,
similar structure.
No. Okay. So isomerization is something we'll be learning in this chapter. So if you're not familiar with it, no issues. So first you'll have like brief introduction, naming isomers, overall thing, like what is the structure like, how it is, how to identify.
Isomers is like when they have the same formula, but the chemical structure or the physical, I don't remember, but that is different.
Correct. Same formula, different structures. Yeah, that's isomers. Once you have that introduction, you'll study about the different preparation properties. How do you prepare that compound? Sometimes if it's like a commercially important compound like alcohols and all, or carboxylic acid, you learn like what are the laboratory preparation methods and what are the industrial preparation methods. Then you learn about the physical properties like boiling point, melting point, what does it look like color, taste, smell, all of that stuff. And finally, you learn about the chemical properties. So chemical properties are all the reactions that it goes through. Okay, so this is the same, what do you call, general structure of every single organic chapter. So we'll have an introduction about it, nomenclature, isomerization, identification, कौन सा functional group है. The second is preparation, and then the properties, physical and chemical properties. That's all there is. And then we talk about uses, but they're like, it's just a tiny bit chapter. Uses are not very important. Focus more on the reactions. So the introductory chapter, why you need to pay attention is, one, we'll be going over the nomenclature. So we'll be talking about the general rules of the nomenclature. So when you study each functional group at a time, that's like one whole section covered. It's going to be more of a refresher or a revision of it. And two, I mentioned that we'll talk about the properties of organic compounds, like what causes them to react in a specific way, right? So when we study about the preparation and the chemical properties, when we're doing the reactions, some of the reactions may get confusing. Like एक ही reactant के साथ minor differences in the catalyst or the reagents that you use will give you two completely different properties. So why is that the case? Like the reason behind it, the anomalies, exceptions that you have, the reaction mechanism, like how does the reaction proceed? The reasoning or the answer behind all of that lies in what we're going to study in this particular chapter. Also, a lot of things like why are certain compounds more reactive? Why are they less reactive? That is due to some special, how the structure is, what kind of bonds they have. All of that we're going to study in this chapter. So this forms like your basic building blocks. So this is kind of an important chapter. Once this is set, rest of your organic will build upon this. It will feel so much more easier and logical. You don't have to learn so many. It's not going to look like a giant puzzle. Like you can figure things out easily. Okay. So the first half of this chapter, so I'll just give a brief structure of what all we have in this chapter. Okay. So the first part is going to be introduction. And this is going to be a rehash of whatever you did in 10th standard about the tetravalency, about the catenation, all of that stuff. Then we look at the hybridization. So this is something you guys studied in chemical bonding, abhi jo khatam kiya. So different carbons, when it's in single bond, double bond, triple bond, what all hybridization does it have? And along with the hybridization, the shape and the bond angle, all of that stuff. Okay. And the third is we're going to talk about the structural representation. Like the different types of structures that the way the different structures are represented. Like one is something like this that you're familiar with. Another type of structure is just the bond line, where you'll just be given something like this. Here it's going to look, it looks just like some scribbles, but soon you'll be able to recognize, okay, what organic compound this is. So those different, and then the wedge and the dashed structures and all that. Next, we look at classification of organic compounds.
So the ones that is like the lines one, each line is like each carbon, right? Like, and then of course hydrogen is there, but each line is one carbon, right? Each point.
No, line is not carbon. Each point of intersection is carbon. So the red color dots that I'm drawing, so that is a carbon. So each line represents the bond between the carbon atoms. Anyway, so when we get to this section, becomes much more clearer. We'll go step by step. So nomenclature, and after nomenclature, we will talk about reaction mechanisms. Actually, along with nomenclature, we'll also look at isomerism. They're closely related. Yeah. So out of all of this, this is very important, the hybridization part of it. Structural representation, I'll put 2 stars to it. This would be just a single star. And nomenclature and reaction mechanisms are the most important. 3 stars. Yeah. So classification, you guys will get the hang of it, not a lot to it. Structural representation, it is just for your own understanding. So that's it. Like, as long as you can figure out where are the carbon atoms, how many hydrogens are there, that's it. Hybridization, there are some properties like the reactivity, electronegativity, all of that stuff directly related to this to some extent. So these are like the main things that you guys need to focus on, especially nomenclature and the reaction mechanisms. These two are the main things. Okay. Adit, you asked about name of the chapter, right? Name of chapter is kind of long. It's some basic concepts and techniques. I think there's a colon, or there's like an like of organic chemistry, or maybe it's the other way around. It's organic chemistry, some basic concepts and techniques. But yeah, it's kind of what this is the name of the chapter. Okay. All right. So you guys ready to jump into?
So I think in further we completed till isomerism. I'm just after that.
Okay. So you kind of like just started or in the middle of like the reaction mechanisms.
It's just about to end it. What is there in reaction mechanisms?
Lots of things. So you have homolytic and heterolytic cleavage, like how the bond breaks. And then you have inductive effect, electromeric effects, like plus I, plus E, minus E, resonance, hyperconjugation.
Yeah, we ended at resonance. Like
Oh,
ma'am was about to explain it properly.
okay. That means like almost 80% of the chapter is done, which because I've done it a lot. Okay. All right. So you guys ready? Can we you guys ready to jump in?
Yes, ma'am.
Yes, ma'am.
Okay. All right. So introduction to organic chemistry. What is organic chemistry?
Chemistry of organic substances.
What do you mean by organic substances?
Like
Uh,
stuff that makes
substances
up the
which have
planet and the
carbon in them.
people and plant and hydrogen and oxygen.
Absolutely. In short, it's basically chemistry of carbon, or like if you had to elaborate on it a little bit, so carbon in living organ or living or related to living things. It could be either living or dead things, not non-living, not like rocks and mud and stuff. So living plus related things. So why I say living plus related is, even when you look at petrochemicals, obviously petrol, diesel, nail polish remover, these are not living organisms, right? But these things you can get from living things. So that's how petroleum is formed, like the plants, dinosaurs, whatever, like billions of years ago, living organisms, when they died, they got buried and then they decomposed, and the end products of that decomposition, we got, now what we have are the simple compounds of carbon and hydrogen and sometimes even oxygen. Okay, so that's organic chemistry. So the center of attention in organic chemistry is carbon. It's basically you're studying how carbon behaves in different situations. You know, when if it is contained, if it is bonded only to hydrogen, so you have hydrocarbons. Carbon bonded in a single bond in double bonds, in triple bonds? What if it is attached to oxygen? What if it is attached to both oxygen and nitrogen in different situations? Okay. And why is carbon so versatile? Like, why does carbon find itself in so many different types of compounds, so many different types of situations? What makes it so special?
It's tetravalency and
Tetravalency.
cantation.
Correct. So tetravalency is one. And the other property is?
Catenation.
Catenation.
Correct. So tetravalency, self-explanatory. Tetra meaning 4 and valency is how many bonds it forms. So carbon is capable of forming 4 bonds, but that's not the only reason. So the fact that carbon forms 4 covalent bonds and it is the right size that it allows, like it forms 4 bonds in different ways. Like it can form 4 individual single bonds, or it can form double bond plus 2 single bonds, or it can form like a triple bond plus a single bond, or it can form like 2 double bonds this way. So whatever permutations and combinations you can find with 4 bonds, carbon forms all of them. So that's like, it's very flexible. Next is catenation. What do you mean by catenation?
Carbon's
Carbon's ability to form like rings and chains of compound.
Correct. So carbon is capable of forming long chains, self-linked chains. Like it can form long chains consisting of carbon alone. So this property is called catenation. And because of catenation, you have like plastics are possible. Like plastics are polymers of carbon compounds. It's like really long chains of carbon. These chains may be single chains, or they may be branched, or they may link to each other. Living organisms are made up of long chains of carbon compounds. So yeah, catenation is another important property that makes carbon like pretty versatile. Okay, remaining 4 bonds you can have like hydrogen or chlorine or whatever it may be. Yeah. So this is another specialty of carbon. This makes it pretty versatile. And because it forms all of these, you can see that this is not possible in any other compound. So if you take metals, metals are electropositive. They cannot form chains. They just form cations and then they just bond with whatever is negatively charged. And they can't even form multiple types of bonds like carbon can. If you take non-metals, the substances that do form covalent bonds, noble gases don't form any bonds at all. They don't react at all. That limits them. If you consider halogens, they are highly electronegative. So even if they do form multiple bonds, they tend to, get reduced into halide ions, or they get oxidized into halide ions. Same is the case with nitrogen and oxygen. They're too small and they're extremely electronegative. So carbon is in that sweet spot where all of this is possible. The next best element that shows this kind of thing is silicon. And you have silicon ka structure also, like quartz is a best example of this. So quartz is just like how carbon forms really long chains. It's like, it's a large network consisting of SiO2 units. So that's quartz. And that is the reason, like it's a popular theory that if you didn't have a carbon-based life form in the universe, another option that you can look for possibly is a silicon-based life form. So yeah, carbon and then just uske niche silicon. Any other element is not capable of it because of their unique chemistry, their atomic number of electrons that they have, and the size of those atoms. They are capable of doing this. Okay. Since we're talking about carbon compounds, yeah, depending on the situation, this gives rise to a lot of functional groups, like the group of atoms that carbon is bonded to. And it's, instead of studying each carbon compound on its own, it's easy to study them as groups. Like if you have carbon compounds, the single bond attached to an OH group, all of them tend to have like similar properties because of this oxygen and hydrogen. So it's easy to study them in specific groups depending on what atoms it is attached to. So those groups are functional groups. Next, coming to hybridization and the shape. So carbon forms different types of bonds. So we'll focus on single bond, when it forms double bond, and when it forms a triple bond. So this is something that you guys have already studied. What is the hybridization of carbon when it forms only single bonds?
Alkanes.
No, what is the hybridization? Not the name of the compound. Like carbon का hybridization क्या होगा? What type of orbitals does it need to form in order to have single bonds?
Sp3.
Can you repeat that, Krishna? It was a little unclear.
So Sp3.
Correct. Why so doubtful, you guys? We just completed this whole chapter on chemical bonding. So when carbon needs to have 4 single bonds, see, carbon atomic number is 6, electronic configuration is 1s2, 2s2, 2p2, right? So s orbital hai, p orbital is incomplete with just 2 electrons. So when it forms 4 bonds, it needs 4 different orbitals. So it's going to be sp3 hybridized. Next, when it needs to form a double bond, what would be the hybridization of carbon in this situation?
Sp2.
sp2. Yes. And hybridization in this situation?
Sp.
sp hybridization. Correct. इसका shape क्या है when it is sp3 hybridized?
Tetrahedral.
So tetrahedral.
That is absolutely right. What kind of a shape is this?
Triangle planar.
Trigonal
Trigonal planar.
Yeah, close enough. And the shape when it is sp hybridized?
Linear.
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 Okay, so these are like the basics. Now let's get in slightly deep. How many sigma bonds does it form? How many pi bonds does it form in this case?
4 sigma bonds, 0 pi bonds.
That is correct. So all the single bonds are going to be sigma bonds. So 4 sigma bonds and 0 pi bonds. In this case, Arnav, how many sigma bonds and how many pi bonds?
3 sigma bond, 1 pi bond.
That is correct. And in this case, how many sigma bonds, how many pi bonds?
2 sigma bonds, 2.
2 sigma bonds and 2 pi bonds. That is absolutely right. Yeah, these are like your basics. See, this you've already done in chemical bonding, which we are revisiting over here. Now, this is important because, yeah, like depending on sigma pi bonds, it decides which bonds are easily breakable, which bonds are not very easily breakable. And based on which bonds are stable versus not stable, the reactions are going to be affected. So between sigma and pi bonds, which bond can you break easily? Like
Sigma.
Pi bond.
Different people, different answers.
Pi bonds.
Sigma is like overlap, और जितना overlap हो सकता है उतना ऐसे overlap हो जाएगा. But when it comes to pi bonds, it's like above and below the axis, right? There's a little bit of adjustments there. So based on that, which bond can you break easily? Like if you had to break one bond, will you go for a sigma bond or will you go for a pi bond?
Pi bond would break easily.
Yeah, pi bond, right? So keep that in mind. So suppose I have an alkene, which is something like this: CH3, CH, and यहाँ पे CH2. And if this particular molecule takes part in a reaction, so I'm going to number the bonds here. To the pi bond, let's say 1. The sigma bond of this is 2. And this bond is 3. So between 1, 2, and 3, which bond is going to break when this goes into a reaction? Which is the most reactive site?
H2C.
Come again, Ritu, can you repeat that? Wait. Let's say the bond between these two is 1 and the bond between these two is 2. So between 1 and 2, which is the more reactive center in this molecule?
1.
Rest of you, is Ritu correct?
Ma'am, could you repeat your question? Your voice was lagging.
So in this molecule, I've numbered the bonds as 1 and 2. Like double bond is 1 and the single bond is bond number 2. So if this were going in a reaction, which is the more reactive site? Site number 1 or site number 2?
Site number 2.
All right, Ritu said site number 1, Kaveri said site number 2. What about the rest of you? Smira, Arnav, Adit, Sanat, Rishit, what do you guys say?
Site 1.
Adit's also going for site 1.
Ma'am, I think site 1.
Okay. Sanat, Rishit, and Arnav?
1.
1. Okay. So whoever said site number 1, what is your reason?
Ma'am, so you said that single bonds have a greater strength than double bonds. So while reaction, the double bond might break easier, so it will be more reactive. So I said 1.
Awesome. Smera, yours is, I'd say 90% correct. Instead of using the terms single bond, double bond, it's more of sigma bond versus pi bond. So sigma bonds are stable, there's maximum overlap. Pi bonds can break easily. Now double bonds tend to have like one pi bond center. So this is the more reactive site. And even when this undergoes reaction, right, the whole bond is not going to break. Only the pi bond is going to break and it's going to form the compound accordingly.
Okay, ma'am.
Okay, Kaveri, got it? What was your reasoning? Like, why did you guess site 2?
I thought that there would be, like, since in site 2 there's only one bond, there would be more, I don't know, like space for other.
That's interesting. So that's something called steric hindrance, and the whole chemistry related to spatial arrangement, that's called stereochemistry. That forms a major aspect which we'll touch on later. But that's a very valid reasoning, Kaveri. But the primary thing is you need to look at which part is electron rich, like which part has a lot of electrons, and which bond seems like it's going to break easily. So between the sigma and pi bonds, the pi bond is going to break easily, which is why knowing the hybridization and this chemistry behind it is important. So that's how you judge what kind of reaction is going to happen and where is the reaction going to happen.
Ma'am, but there are in the first one there's 1 sigma 1 pi. In the second one there's 1 sigma. So even if 1 pi is like an additional thing that can be broken easily, there are still going to be 2 sigma bonds, right?
This whole
Like
molecule, there are multiple sigma bonds and there's a single pi bond.
1 sigma bond, 1 sigma bond. So both are kind of equal that way, right?
No,
I mean, like in one there's 1 sigma bond and 1 pi bond, and in 2 there's 1 sigma bond. So we are saying that pi bond can be broken easily. That's why the first one is more reactive. But then even if the pi bond is broken more easily, we still have 1 sigma bond, right? And
Yeah.
in 2 also we have 1 sigma bond. So isn't that kind of the same?
Yeah. No, what is your point? Like the pi bond is there, that's what makes it more reactive. Suppose I had only sigma bonds, if I had CH3, C, and H and H. So if I had this kind of a thing, both of these are equivalent, both of these are sigma bonds. So it like both of these are equally reactive. Like if I had another agent attacking it, there is equal chance of that reagent attacking either this carbon or this carbon.
So it will occupy the space that was occupied, like it will be instead of the pi bond, wherever the pi bond was.
No, in this
Like
case, there is no question of pi bond.
No, when there is a pi bond.
When there is a pi bond, then 100% it's going to attack the pi bond only.
Okay, got it.
Yeah, good. Yeah, so that's kind of how you need to look at it. That's how the reactivity and all are decided. All right. Okay, now we have Sp3, Sp2, and Sp. Now, this is something we discussed long ago when we were doing atomic structures, learning about orbitals. But do you guys remember what is the order of electronegativity between S, P, D, and F? Out of these 4 orbitals, which orbital can attract electrons the most? Like which has maximum electronegativity? Do you guys remember?
P.
Sanat, how do you answer that?
Because like a lot of the electronegative elements are in the P block.
Oh, D block or P block? What did you say?
P.
P. Oh, that's interesting. But when you're taking individual orbital, it is not equivalent to comparing it to the whole element. Because if you're looking at electronegativity of elements, the nucleus is the reason. Like the size of the atom, because the atoms are small, they are capable of holding on to the electrons more easily. Like the size of the whole atom and the nuclear attractive power comes into the picture. But when I'm purely comparing only the orbitals, so I have S orbital, which is spherical, and I have P orbital, which is like dumbbell shape, and then I have the D orbitals, which are again, they have this whole different orientation to them. So if I'm comparing only the S, P, D, and F, which one can attract or hold on to the electron cloud the most between these?
Ma'am, can I try?
Yeah, go ahead.
I'm not sure which one could attract and hold the most, but I remember you were asking like electronegative.
Yeah, that is electronegative.
So I think it's D.
No. So I'll give you guys the
For holding one, I think it should be the S because it would be the closest to the nucleus, right?
absolutely. Rishit, you're right. So it's not just being closest to the nucleus, it's also the shape of it. Like if you guys remember the shielding
Linked to
effect.
shielding effect.
Sorry.
Yeah. I was gonna ask, is it linked to shielding effect?
Correct. Yeah. Shielding effect and the penetration power. S has maximum, it can hold on to the electrons maximum, like it's the electron cloud is uniformly distributed and all that. So electronegativity of S electron is more, followed by P, followed by D, followed by F. Okay, so we're talking only about the orbital. So you just need to compare the orbital geometry and the property against each other. So don't confuse this with the overall elements itself, not related to S block, P block, P block elements. Okay. So
Then
F,
in S, if the shielding effect is more, then
it's the least. F, D and F is
I'm
very
saying S.
S. Okay, yeah.
If the shielding effect is more, so it will attract more like that.
It's not directly related to shielding effect, but the reasoning behind shielding effect is same as the reasoning behind the electronegative nature. You can think of it that way.
Okay.
Yeah. So yeah, S orbital has maximum electronegative nature, followed by P, followed by D, followed by F. Okay. So this is the order of the electronegative tendencies. So going by this, if you compare an sp3 carbon versus an sp2 carbon versus sp carbon, which particular carbon is going to show the most electronegativity? Like which of these three carbons is going to hold on to the shared pair of electrons the most?
SP.
SP, yeah.
Okay. What are your guys' reasoning? Why do you think it's sp?
SP has like a triple bond, and that's really hard to break.
Yeah.
You guys are right that this particular carbon is going to be the most electronegative, but the reasoning comes from the hybridization. So the triple bonded carbon has sp hybridization, which means that it has two sp orbitals. Abhi, if you compare sp versus sp2 versus sp3, percentage S character, which one has maximum S character?
The linear one, 50%.
This one has 50% S character. This one has 1/3, kitna? 33.33%. And this one is 1/4. This has 25% of S character. So Sp has maximum S character, which shows maximum electronegativity. So that's the reason why this shows maximum electronegativity. And that directly relates to other properties of a triple bonded carbon. Basically, you know, like if you have a triple bonded carbon, like let's say you take ethyne, because this carbon is most electronegative, it can hold on to the shared pair of electrons the best, which is why this is going to show acidic properties. Acidic property matlab it can easily lose this electron, and this carbon is going to be negatively charged, and because it's losing a proton, that's where your acidic character comes from. Okay. So why are alkynes the most acidic out of alkanes? Alkynes is coming back to its hybridization, because alkynes have sp hybridized carbon, and sp hybridization, because they have maximum S character, they tend to show maximum electronegativity. So if electronegativity is a lot more, this carbon can hold on to the shared pair of electrons more easily, which means it can let go of this hydrogen more easily. So if the hydrogen is going away as an H plus, that is basically your acidic behavior. Like releasing H plus ions is the definition of being acidic. So that's why your alkynes are most acidic.
Ma'am, could you repeat that part again?
Which part, Rishad?
So the breaking and giving away.
So okay, I'll just repeat the whole thing again. That's basically the whole story of it. Okay, so if you compare sp3 carbon versus sp2 carbon versus sp carbon, sp carbons tend to be the most electronegative. Why are they the most electronegative? Because of that hybridization. Sp hybridized carbon have, like, those hybrid orbitals have maximum s character, and s orbital being the most electronegative of all, that contributes to sp being the most electronegative hybridized orbital compared to sp2 and sp3. So let's say you have ethene versus ethine. If ethene loses, like if this bond is broken versus if this bond is broken, which carbon can hold on to the electrons better? Ethene or ethine?
Ethine.
Fine.
Ethine. Yeah, Rishad?
Yes, ma'am, time.
Ethine, right? So if this can hold on to its electrons better, when this bond breaks, it means that it's holding on to the electrons. So this one will get a negative charge, and the hydrogen is breaking away as H+. So hydrogen is not getting any electrons. This particular carbon, being more electronegative, will take away both the electrons. So if ethine is breaking into an anion plus H+, what sort of a behavior is that? Like, where do you see such kind of behavior? Like, what do you call those compounds that release H+? Yeah, Rishad?
The ones that release hydrogen.
Huh? Can you think of other compounds that tend to do this? Jahan se H+ aata hai? The ones that give out H+?
Acids.
Acids.
When you put them like in water.
Yeah, HCl, H2SO4, all of these release H+, no? HCl breaks into H+ and Cl-. H2SO4 breaks into H+ and SO4 2-. Remember that, Rishad?
Yes, ma'am. So only I had to say acid.
Yeah. So that's why ethine shows the most acidic property, or ethine is the most acidic out of all the hydrocarbons. Like if you compare it to any alkene or any alkane.
But then even ethene is releasing hydrogen, right?
It's not. That's a thing. Like ethine, because of its electronegativity, it has the possibility to do that. Ethene doesn't. Like this carbon is not electronegative enough to, hold a negative charge here. It's not that.
Because
Yeah.
hybridized.
Yeah. Okay. So that's like acidity of ethine is an important chemical property that we're going to study about. And that comes due to hybridization. That's why I need you guys to be familiar with these properties. One, depending on what kind of bond carbon has, what is its hybridization? And two, what is the importance of this hybridization? The main thing being the order of electronegativity. So Sp has maximum electronegativity, followed by Sp2, followed by Sp3. So this is the order of electronegativity. Yeah. So when it comes to hybridization, three things you guys need to know. So based on the structure, figure out the hybridization. From the hybridization, automatically you should know the shape, you should know the reactivity, like which is the reactive center. So if you have double or triple bonds, those centers tend to be more reactive than your single bond centers. And 3, you need to know the order of electronegativity. Okay. Clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay,
Yes, ma'am.
noted. Like, have you noted all 3 of them? Like, have you noted the shape, the reactivity, and the electronegativity?
Yes, ma'am. Noted.
Just one second.
Huh. Yes, let me know if you're done, and if you're reacting to it, like keep it, because if you react and then if you take it away, I might miss it. So either put it in the chat or, yeah. Okay, Kaveri is done and Arnav is done.
Just 1 second, ma'am. Last point.
Okay. Arnav, that's what I was saying. I think you just reacted and you took it away. Like, don't do that. Yeah.
So in electronegativity, we can either say as SPDF or SP, Sp2, Sp3.
This is the more important thing. Like, note this one down. If you want, you can put this on the side for your information type. Now, because S is more than P more than D, that's where this is coming from.
Ma'am,
Sure.
it's just electronegativity, and sorry, the S is more electronegativity because it attracts the electrons, right? That is why it is the most electronegativity.
It has a tendency to hold on to the electrons the best.
Is it not related to attraction of the electrons?
No, because S orbital is an electronic orbital, right? It's not going to attract charges the way proton on a nucleus does. So when we talk about orbitals, it's the tendency to hold on to those electrons the most.
Okay.
Okay. All right. Guess all of you are done. ठीक है. इसके बाद we look at different types of structural representation. I think this is the last thing we'll do today. 20 minutes में हो जाएगा. So classification and then nomenclature, we can start fresh tomorrow, like next class onwards. So structural representation is purely like, how do you represent organic compounds on paper? This is what we'll be talking about. So you won't get like questions based on this. It's more of, it'll automatically be there in the questions and you need to learn how to identify it. Okay. The first type of representation is, it's called complete structure, but this is what you guys have come across in 10th grade. Complete structure is, again, like if you have a structure, it is completely expanded and represented. So for example, if you had a compound, let's say butane. Do you guys remember what is butane? Yes, no?
C4.
C4H10.
Nice, you remember it. Good. C4H10. So 4 carbon atom member is butane, all single bonds. It's a hydrocarbon. So complete structure mein, this is how you represent it. So again, for all the different types of representations, I'll take butane only. I'll just keep it here. So in the case of complete structure, you show all the carbons, like the bond between them, and then you show all the hydrogens also with the bonds. So when you're expanding each and every, when you're showing the bond between each and every atom, including the hydrogen, oxygen, like if you're expanding everything, that's the complete structure. Next, you have condensed structure. This is what we'll be working with the most. At least I personally, I'm never going to use this again. Takes a lot of time, maybe in the beginning for a bit, but this is what we'll be working with the most often. So condensed structure may, you show the bonds only between the important atoms, only between carbons and maybe the functional groups. So remaining filler atoms like hydrogens, you're going to condense it. You're not going to show the bonds between them. So condensed structure is going to look like this. So you have carbon. You're not showing the bonds between carbon and hydrogen. So this is going to become CH3. So if I write CH3, automatically assume that this carbon is bonded to 3 hydrogens. I'm just not showing it on paper. So CH3, CH2, CH2, CH3. When you're showing each and every bond, that's a complete structure. When you're ignoring the bonds between the filler atoms like hydrogen, when you're showing the bonds between the important atoms like only the carbon, so that's the condensed structure. It's the condensed form of the original structure. And the third one is, it's called bond line structure. Bond line structure may, it is shorter version of the condensed structure. So bond line may, you are literally showing only the bonds in the form of lines. You're not representing any atoms. So if it's a 4 carbon atom structure, you draw 4 lines. So 1, 2, 3, 4. So in the bond line structure, you don't show carbon and hydrogen. The points of intersection and the end points represent that there is a carbon atom. I made a mistake here. Yeah, 4 carbon atoms actually. So 1, 2, 3, 4. So because there are 4 points of intersections and the end points. So these represent carbon atoms. You don't explicitly talk about how many hydrogens are there. So hydrogens, number of hydrogens, it's automatically assumed. Like for example, यहाँ पे एक carbon है. Because this carbon has 2 bonds here and here, automatically assume that remaining valencies are filled up by hydrogens. So carbon के लिए 4 होना चाहिए. 2 of them bonded to other carbons, which means that remaining 2 of them bonded to hydrogens. यहाँ पे CH2 होना चाहिए.
Double or triple bond.
If there is a double or triple bond, yeah, that's a good point. Suppose I want to show butene. This is a 4 carbon atom. Ene hai, matlab there is a single, like there's a double bond somewhere in the structure. So double bond is represented by 2 lines. So 1 carbon, 2 carbon, next 3 carbon, third carbon here, fourth carbon here. So this is how it is represented. And agar triple bond butane को represent करना है, then you have a triple bond. Now, because this particular carbon has sp hybridization, it's going to be linear. So the next one is going to be like this. So 1, 2, 3, and the fourth one is going to be like this. This is how butane is represented. How you interpret this is that ट्रिपल बॉन्ड है, मतलब यहाँ पे एक कार्बन होना चाहिए, यहाँ पे एक कार्बन होना चाहिए, then there's a single bond here and a point of intersection here. So there is a carbon over here and there is a carbon over here. Now you can see that this carbon has a triple bond, मतलब it is pending one more bond, tetravalency fulfill करना है तो automatically assume that okay, 3 bonds are with other carbon, single bond is fulfilled by hydrogen. Now this carbon has all 4 bonds fulfilled, 3 here plus 1 here. So this carbon will not have any hydrogen. This carbon 1, 2. So remaining 3, 4 by hydrogen. So this has H2. And corner mein jo hai carbon, only 1 bond is filled, which means that 3 more are filled by hydrogens. So you don't explicitly show carbon and hydrogen. The end points are all carbons, like the points between the bonds are all carbons. And hydrogen is filling up whatever remaining valencies are there. And another important point is you show other atoms other than carbon and hydrogen. Like if there's an oxygen, if there's a hydrogen, if there's an oxygen or nitrogen or any other carbon, which is any other atom which is not carbon or hydrogen, you explicitly write it. Yeah, Ritu, what's up?
I have a doubt in the butane structure. Won't it have like another double bond?
I'll say, okay, let's say this is 1 butane. So 1 butane, so first position, like first carbon pe, there is 1 double bond. So if you're talking about 2 double bonds, then that becomes butadiene. So diene represents that there are 2 double bonds. Butane has only a single double bond. So double bond, this singles, that's it.
Ma'am, could you like write once again, like butane has 4 carbons and those are again the list. Propane has 5, those are.
I'll revise that when we do the nomenclature. Here, just learn how to recognize the structures. That's the main thing I want you guys to take away from this. Names and all, I'll revise it when we do nomenclature. There it'll get clearer. But here, if I give you a random scribbling like this, you guys need to know how many carbons are there, how many hydrogens are there. So if I write it like this, okay.
Is that propanol?
1, 2, 3, 4 carbons hai. So this would be butanol. So when I have a structure like this, because I wrote oxygen here, it means that ye bond ke aage, this particular carbon is bonded to oxygen. So this end point doesn't have any carbons. So this over here in this place, there is oxygen. Other points of intersection as usual, they're all carbon atoms. And to fulfill the valency, those many number of hydrogens are there. That's it. This is another, like benzene mostly is represented by bond line. It was called nitrobenzene.
Ma'am, why is there a circle in between of benzene?
Oh, so, okay. Or I'll put it this way. Like when we do resonance, it gets clearer. Okay, this is a structure of benzene.
Okay.
Benzene has a resonating structure, like double bond. They're alternating between either these three, or you can find them in these three also. Like they're constantly moving. The double bond are constantly moving, and because of resonance, you end up representing the whole thing as a circle. Smera, you were saying something?
I was saying that I have the same doubt.
Benzene.
Got it.
Yeah. Condensed is what we'll be using the most out of all of these. Bond line, you may come across it if you're practicing anything online, or generally internet pay, the most I've seen it is like bond line structures. So we'll have lots of practice with this also. Complete structure, you will not come across this, I can promise you that, unless it's like methane or something really simple. Okay. Yeah, condensed is what we'll be using the most. But learn to identify bond line also. So suppose I have this. This is benzene. And then if I just put it like this. So this means that 6 carbon ring structure, closed ring. फिर यहाँ पे एक carbon है, यहाँ पे एक carbon है, यहाँ पे एक carbon है. If I put Cl over here, it means that there is a chlorine atom attached. So this is not carbon anymore. Only 2 carbons are attached, and there is chloride atom over here.
How many carbons are there?
2 carbons. So this point of intersection is 1 carbon, and this is 1 carbon, apart from the 6 carbons in benzene, of course. 2 carbons here, and chlorine is over here. Suppose I didn't put chlorine, if I just leave it like this, then it means that there is a carbon over here also.
So the center, like that carbon, it is bonding with 1 chlorine, 1 carbon, and another carbon. So we'll just assume that there's 1 more hydrogen.
Yes, correct. So wherever bond line wherever it feels like incomplete hai, then assume that that filler is hydrogen is basically a filler in all of organic chemistry. Agar kahin pe bhi bonds fulfill nahi ho raha hai, assume there's a hydrogen that way. But if I add 1 more, it means that this carbon has all 4 fulfilled, so no hydrogen here. Okay, so these are like the different structural representations. Next, when it comes to Sp2 and Sp3, so Sp2 is trigonal planar, so all 3 bonds or all 4 bonds are in the same plane. So 2D mein you can easily represent it. Same for Sp hybridization, it is linear, so you can like represent it on paper. This is going to be the exact shape of it. But when it comes to Sp3, 4 bonds are in tetrahedral shape, right? So it's a 3-dimensional shape. How do you represent it on 2D paper? So to get that 3D effect, if these 2 are in the same plane, the other 2, one is going behind the screen and one is coming in front of the screen, right? So whichever is behind the screen is represented by in the form of dashes like this, and whichever is coming in front is represented by a solid wedge like this. Okay, so if you see this kind of representation with a dashed line and a solid line, the solid line represents that it's coming out in front, and this dashed line represents that it's behind. So like I showed you in a video. Let's say these are the 4 bonds. ऊपर एक है. These two are in the same plane as the page. एक ही plane पे है. Then number 3 and number 4, one will have to be forward and one is behind. Right? One is forward, one is behind. So पीछे की तरफ जो है, that is represented by dashed notation, and आगे की तरफ जो है, that is represented by a solid wedge. Because all four of them, it's not possible to represent in 3D, right? So two of them that are in the same plane are represented by the regular lines, and number 3 and number 4, पीछे की तरफ जो है, that's dashed, आगे की तरफ जो है, that's solid.
Ma'am, so like any of the lines can be dashed or like solid, right?
Specifically, the one that's behind is dashed and the one that's in front is solid.
But like when we are drawing,
Hmm.
it can be any of them, right?
I didn't get you. Matlab, I can't
Like,
have, like, if I draw it like this, it means that both of them are going away from each other. If both of them
no,
are,
like
the other two,
there's only one which is going behind, but like it can be any of the bonds, right?
correct. Yeah. So I can have it represented like this. Agar is taraf these two are in the plane of this thing, then this will be piche and this will be solid as well in front. Yeah, red mein whatever I've drawn is exactly what I'm showing here. These two are in the same plane, and एक पीछे की तरफ है और एक आगे की तरफ है. The blue one I was showing is in this orientation. These two are in the same plane. And इस तरफ एक पीछे की तरफ है, एक आगे की तरफ. Yeah. It's just to show the 3D representation. This I can turn it around. If I turn it around this way, these two, let's say these two are in the same plane, then yes, again, like Sp3 hybridization, matlab these four are always in tetrahedral, right? So it's a matter of from which angle are you viewing the tetrahedral. So two of them, you keep it fixed in the same plane, and the other two automatically always one will be aage and one will be piche. One is represented with dash notation, one is represented with solid notation. Okay. So this is how you represent the thing. So while writing on paper, either you can write down the complete structure, but that's used only for like absolute beginners who are just learning about organic chemistry, for really young learners. But as you, and also it's a huge waste of time, like to expand each and everything. So a better way to denote it is the condensed structure. This is what you'll be using most of the time, condensed structure. When we're doing reaction mechanisms, then we expand like a part of it, but general representation is always like condensed structure is what we'll be using. But you will also come across bond line pretty frequently. So you will need to like focus on learning both of these. Condensed is pretty self-explanatory, but bond line is what you'll need a little practice in. Okay. And 3D structures, the way you represent is using dash and solid wedge. So these are like basics. Next class, we look at exclusively like classification, nomenclature, and the different electronic effects, reaction mechanisms.